module 8 on numerical solution of Navier-Stokes equations. So this module represents the heart of our CFA, that is to say the application of the techniques which we have learned so far, their application to solution of real life flow problems. So in this module we will have a brief look at the fundamental features of Navier-Stokes equations, what differentiates them from the generic transport equations which we have solved earlier using finite differences, finite volumes and finite element methods. And then we will have a look at explicit and implicit time integration techniques as they are applied to the solution of incompressible Navier-Stokes equations. And we would look at implicit pressure correction methods which are popular for the solution of steady state problems, and we will also look at fractional step methods. Now this module would make use of all the knowledge which you have gained earlier on discretization schemes, that is finite difference, finite volume or finite element method, time integration techniques and the techniques for solution of algebraic equations. So, we will not go into details of the spatial discretization using a particular technique or a particular time integration scheme or use of a specific algebraic equation solver. We would focus on the fundamental algorithms and fundamental features which we require in the solution of Navier-Stokes equations. So, we will presume that the user is familiar with a particular discretization scheme, finite element, finite volume or finite differences, that choice has been made, and then which are the explicit and implicit time integration schemes which one can use and what are additional things which are required in the solution of Navier-Stokes equations. Now in the first lecture we would focus on the spatial features of Navier-Stokes equations, what differentiate these equations from the solution of ordinary single variable transport equations. So what are the spatial features that would form the crux of today's lecture? We will look at the different types of grid arrangements which we can use in Navier-Stokes equation, which is facilitated by the nature of the equations. In particular, we will have a look at what is called collocated grid arrangement and what is meant by staggered grid arrangement in particular context of structured finite difference or finite volume discretization schemes. Then we will have a brief look at the numerical simulation of incompressible flows. In particular, we will derive one equation which is essential in the solution of incompressible equations, and it does not come directly from our conservation laws, which we call Poisson equation. And we will have a brief look at the numerical simulation of compressible flows just in a generic fashion. Now what are the spatial features of Navier-Stokes equations? When we looked at Navier-Stokes equations, what we call them is essentially our momentum equations for a Newtonian fluid, and momentum equation is a vector equation. So that essentially means that Navier-Stokes equations are a set of 3 coupled partial differential equations. It is not a single equation in contrast to our scalar transport equation, and in addition it must be solved along with the continuity equation and energy equation. So this is what differentiates the Navier-Stokes solution from the solution of a transport equation, or let us say simple heat conduction problem. In fact, in CFD literature very often when we talk about Navier-Stokes equation, what we mean is we mean the collection of continuity, momentum and energy equations taken together, because all of these must be solved, all of these are coupled and they must be solved together to obtain our flow variables, that is to say the velocity components, density, pressure and temperature. Now yet another remarkable feature which we can observe is that each conservation equation can be recast in the form of generalized transport equation, which contains a time derivative term, a convective term, a diffusive term and a source term. To clarify this point, let us have just brief look at two of the equations, the continuity equation and the momentum equation in the vector form, and let us see whether our contention holds good or can we recognize the similarities between Navier-Stokes equation system and our generic transport equation. So, first let us write our generic transport equation. Del of rho phi over del t plus divergence of rho v phi is equal to divergence of gamma times gradient of phi, plus we had a source term called q phi. So, the first term, this was our temporal derivative, this is what we call the convective term, this was our diffusive term, and the last one was our source term. Now, let us have a look at continuity equation. Del rho by del t plus divergence of rho v is equal to 0. Now, if you compare the two equations, this generic scalar transport equation and our continuity equation, what we can observe is simply if we put phi is equal to 1 and gamma and q phi as 0, we get our continuity equation. So, the continuity equation also has a temporal derivative term and a convective term. We can assume here that gamma is equal to 0 and q phi is equal to 0, but in form it is very similar to our generic transport equation. Similarly, let us write our momentum equation. Which we also call say Navier-Stokes equations. Del rho v by del t plus divergence of rho v v minus gradient of p plus divergence of tau plus rho times p. So, once again if we compare this equation with our generic transport equation, the similarities are obvious. We got a time derivative term, a convective term, stresses there if represent our diffusive term, and this body force could be taken, body force along with the pressure gradient. These two can be combined together in the form of what we call a source term. Okay, so form of these continuity equation and momentum equation is very similar to that of our generic transport equation, and that would allow us to make use of the steps which you learned earlier for numerical solution of generalized or generic transport equation. So, that is why we said that each of the conservation equation can be recast in the form of generalized transport equation, which contains a time derivative, a convective term, a diffusive term and a source term. So, all that it means is that we can choose a specific technique, let us say for spatial discretization and for time integration, which we have earlier learnt for the solution of scalar transport equation, and that scheme can also be extended rather easily for the solution of full set of Navier-Stokes equations. Now, if we deal with compressible flows, in the compressible flow continuity equation, it is essentially a transport equation for density, the del rho by del T, that is time derivative for density, and plus divergence of rho times V, that gives us the convection term for the density. Momentum equation, that represents a transport equation for velocity, and energy equation represents a transport equation for either total energy, or we can also transform it into the transport equation for temperature. So, in fact, in the case of compressible flows, it's rather easy for us to combine these set of equations, this continuity equation, momentum equation, and energy equation in form of a generic vector equation representing transport of a vector quantity, and apply a solution technique to solve this set of equations. So, all that we need to do in this case is discretize each equation, solve the collection of resulting discretized equations which are non-linear, and we have to supplement our equations though by equations of state. For instance, we have pressure coming into the momentum equation, we have got viscosity, we have got thermal conductivity coming in energy equation. So, we need to supply additional equations for the evaluation of these properties. Equation of state is required for computation of pressure. We also need equations which will give us temperature dependent viscosity and the thermal conductivity to enable us to solve the compressible flow problem. But as far as the conceptual solution procedure is concerned, that is very simple, that since each equation represents a transport of a particular quantity, continuity equation represents transport equation for density, x momentum equation is transport equation for, let us say, rho u, y momentum equation will give us a transport equation for rho v, z momentum equation will give us transport equation for rho w, and energy equation will give us the transport equation for, let us say, total energy. Discretize each one of them separately using same set of discretization procedures and time integration schemes, and solve them sequentially. If in fact, if you are using an explicit solver, the solution becomes very simple. We do not have to use a sequential iteration scheme in that case. So, this in algorithmic terms, the algorithm for numerical solution of unsteady compressible flows is relatively straightforward. Of course, there are issues which we will have to take care of when we go to hypersonic compressible flows. There would be formation of shock waves which have to be accounted for. So, the solution process would be a bit involved. We have to take extra care in that case. We are not going to discuss those issues in this introductory course, but nevertheless, if we can choose fairly small time step and a good quality, a fairly defined mesh, we can solve a compressible flow, compressible Navier-Stokes equations for any Mach number without much fuss. Of course, that will involve huge amount of investment in terms of the computational time. Next, let us have a look at incompressible flows. For incompressible flows, again, the governing equations are in the form similar to the generic transport equation, with one difference here, that in continuity equation what happens is, it's not a dominant equation in terms of density. Density here is constant, that we know. So, it's the continuity equation cannot be said to be a transport equation for density. Similarly, there is no equation of state. Since we do not have equation of state like P is equal to rho RT for an ideal gas involved in compressible flow simulations, then how do we get at pressure? And we do need gradient of pressure in our momentum equation. So, this particular feature is what requires special attention for the solution of incompressible flows, and that would be one of the issues which we are going to address today. Okay, so, let us remember that in the case of incompressible Navier-Stokes equation, there is no equation of state which relates pressure, temperature and density, and in this case continuity equation reduces to what we call a kinematic constant on velocity field. We will have to say that divergence of V is 0. So, velocity field which we get as a part of a solution process should be such that it is divergence free, which is essentially a kinematic constant, it is not a dynamic constant. But nevertheless, for the satisfaction of continuity, this kinematic constant must be satisfied by the velocity field which we compute numerically. So, there are two issues, that how do we get pressure and how do we satisfy this kinematic constant imposed by the continuity equation we would address specifically today. Now, what are other features? If you can go back to the mathematical classifications which we dealt of conservation equations which we dealt in module 2, we said, look, Navier-Stokes equations, they are non-linear coupled equations and they have got what we call a mixed nature. Given incompressible Navier-Stokes equation, if we say steady state, then we say it is elliptic equation. If it were unsteady, we say its nature is parabolic. When we go for compressible flows, the situation becomes even more complicated. That classification of equation would depend on the basis of local Mach number of the flow. So, even if you are dealing with a steady state problem, there could be regions of flow where the equation is elliptic in nature, there are other regions where it becomes hyperbolic. So, the equation is mixed, and coming up with a single numerical simulation algorithm for a mixed equation is rather difficult. We also saw one feature, that if you look at unsteady Navier-Stokes equations, the situation is slightly better, specifically with respect to time. Unsteady Navier-Stokes equations for incompressible flow, they are parabolic in nature. Similarly, unsteady Navier-Stokes equations would become hyperbolic for the case of high speed compressible flows. So, this is something which we can utilize or we can exploit in the numerical solution, because here now the nature is much simpler, it is not a mixed nature, so either parabolic or hyperbolic in time for incompressible or compressible flows respectively. So, can we make use of this particular thing? So, that is why we have this, there are numerical difficulties which are associated with the solution of purely elliptic in the case of steady state incompressible flows, or mixed PDEs in the case of compressible flows or compressible Navier-Stokes equations. We rarely attempt to solve the steady state Navier-Stokes equation in either case. In fact, Navier-Stokes equations are mostly solved as an unsteady problem, even if the flow is steady, using a time marching scheme. And what we say, that we have to integrate in time for fairly long time instants. So, long time solution is what would be, or this long time solution of this transient Navier-Stokes problem would yield us the solution of actual steady state. And this methodology is universally used in the solution of Navier-Stokes equations, whether we are dealing with incompressible flows or compressible flows, that we would always solve a steady state flow problem as an unsteady problem. If a steady state solution is our only aim, we would normally use implicit time integration scheme, which will allow us to use large time steps to reach the steady state very quickly. Now, Navier-Stokes equations, they are governing equations for a vector field, and together with this, with velocity, we have got energy equation, which is a transport equation for a scalar field. We have got a scalar variable pressure involved in Navier-Stokes equations. For compressible flows, continuity equation brings a times the scalar variable, that is density. So, here we have got a mix of scalar and vector variables. Okay. Now this mix allows us more freedom in the choice of grid used in numerical simulation. So what are the popular grid choices which have been tried? Let's have a look at them. Now the choice of the grid would also depend on the discretization scheme, that is to say whether we have chosen finite difference method, finite volume method or finite element method. But we can classify the choices broadly in two categories based on the arrangement of our flow variables on grid nodes. The first one we call co-located arrangement, and the second one is called staggered arrangement. So what is a co-located grid? There are two alternative spellings which we use for co-located, either C-O-L-L or C-located. The second one gives us a clearer picture. This is everything is located together. Co means together. So if all the variables, that is to say our velocity components, density, pressure, temperature, they are stored at the same set of grid points, then the grid is called co-located grid. And in this case, there is considerable simplification in programming, and specifically if you want to use advanced or what we call fast solvers based on multigrid methods, there we need to use restriction and prolongation operators for hierarchy of coarse grids which we use. So if the same set of grid nodes are being used for all the variables, we can use the same restriction and prolongation operator for each variable, whether it is your velocity components or temperature or density. So that's one of the advantages which we get in the case of co-located grids. Before proceeding further, let's have a graphical look at what do we mean by a co-located grid. So first let's take a case of structured grid which we might use in finite difference or finite volume formulations. And suppose we take, for instance, let's take a vertex based grid. This is finite difference or finite volume grid, vertex based. So let's use two symbols. We will use this filled circles. Filled circles would represent the grid nodes for scalar quantities. For example, our pressure, temperature and density. We are talking about co-located grid. The same grid points would also be used as the grid nodes for velocities. So let's use arrows to indicate. So this is x velocity component, this is y velocity component. So what do you see? The same grid nodes are being used to store our scalar variables as well as these vector components u and v everywhere. Analogous pictures you can draw for 3-dimensional case. Similarly, if you are using a cell centered formulation, that is your computational node is at the center of a cell, So, that is where all our problem variables or flow variables are defined, that is to say at the centroid. So, filled circles to represent the scalar nodes, and similarly here our velocity components are also defined at these cell centroids. The situation is a bit more complicated in the case of finite elements, though theoretically. So, this again our FDM or FVM cell centered co-located grid. Theoretically, for finite element, what we would say that suppose let us say we have got triangular elements in theory set, the scalars will also be defined here and our velocity components will also be defined at these nodes. Why is it theoretically? Because there are certain requirements which the finite element interpolations should satisfy for pressure and velocity, which would not allow the use of the shape functions of the same order for both pressure and velocity components. But just for the sake of explanation of co-located grid in the context of finite element, if you were supposed to choose, that is what we have to take there. Okay, so this co-located grids, they were tried, they have been popularly tried in unstructured finite volume schemes, and there was a major disadvantage of these schemes is what we call lack of pressure velocity coupling, which might lead to what people call as oscillations in pressure field or checkerboard pattern for the pressure field. Now, this was a situation a decade or so back when these schemes were used extensively for the first time. The recent developments have been able to deal with this problem of checkerboard pattern, and with the advent of or the popularity of what we call unstructured finite volume mesh for CFD simulations, co-located grids are back in favor in numerical simulation of Navier-Stokes equations. Next, let us have a look at what we call staggered grid. Now, here velocity components and scalars are stored at different set of nodes. So, if that is the situation, then we would say the grid is staggered grid. So, the basic definition is that if velocity components and scalars are stored at different set of nodes, then the grid used in CFD simulation would be called a staggered grid. In finite difference or finite volume simulations, what we would normally choose is that the pressure or the scalar nodes, they would lie at the centroids of the grid cells, and velocity nodes are located at the center of respective cell faces in the case of finite difference or finite volume method. And in the case of finite element, we will have to use separate set of elements. For instance, we will use for example linear element for pressure and quadratic element for velocity. Let us have a look at a graphical representation of staggered grids. Let us draw, for the sake of simplicity, a structured finite volume or finite difference grid. Now, the centroids are the ones where pressure or temperature would be defined. That is where we are going to solve for all the scalar components. So, filled dots, they indicate computational nodes for scalar flow variables. For example, pressure, density and temperature. The velocity components would be defined, their nodes would be defined at the cell faces. So, that is where the locations of u velocity components. And similarly, these faces for v velocity component, that is where the computational node for the v velocity component would lie. Okay, if you want to have a look at how the finite volumes would look like for each of these components, let us redraw this figure and illustrate each finite volume separately. So, for a scalar variable it is very obvious, this whole cell, this is our control volume for scalar quantity. How about vu velocity component? How would you define that control volume for that? So, let us draw it separately, another box here. So, this is where, suppose this is one of the u velocity nodes. So, its corresponding control volume would be this. So, with respect, for instance, this is a P, this becomes the east face, this is the west face, south face and north face for a scalar control volume. For control volume for u velocity component, this is, let's call it as Pu. So, this becomes our eastern face for u, western face for this. So, let us hatch it differently. Similarly, southern face and this is northern face. So, this is Cv for u velocity component. In the same way, for the sake of clarity, let us extend this figure further here. Scalar nodes. So, the faces of v velocity component will pass through the scalar nodes. So, let us use vertical hatching to indicate that now this is the Cv for v velocity component. The computational node and the other faces, east face, west face, south face and northern face. for the control volume which you would use in finite volume formulations for V velocity component. So, what we clearly say here that the computational nodes for each velocity component is at different location. In finite volume formulation, we will have to use separate finite volumes for a scalar variable and each of the velocity components. So, that would introduce lots of bookkeeping that will make our algorithmic part of programming component bit complicated. But there is a tremendous advantage which we can see if you look at the first figure which you have drawn here, that traditionally what we think that velocity field or the flow is driven by the difference of pressure. So, at velocity at any node, that is because of the pressure difference at adjoining two computational nodes. So, that is why this particular grid arrangement gives us what we call very strong pressure velocity coupling. Now, similarly, if you are dealing with finite element, then you would use linear elements for pressure this is Fe for pressure, and for velocity we will have to use a quadratic element this is quadratic element for velocity. The advantage I just mentioned that there is strong coupling between the velocity and pressure field, because of which this grid arrangement has been the most popular in CFD analysis. And disadvantage, we have to do elaborate bookkeeping, and if you want to use multi-grid for the solution of each of the flow variables, then we have to maintain separate set of multi-grid operators. But notwithstanding this disadvantage of elaborate bookkeeping and having separate set of operators, the advantage which is offered, that is very strong motivation, and even today staggered grids are used in preference to co-located grids in the context of structured finite difference or finite volume analysis. Now, let us come to the numerical simulation of incompressible flows. This one problem which we mentioned earlier, that Navier-Stokes equations for incompressible flow, they involve a term pressure gradient, this gradient of P is there, but there is no equation for pressure, in contrast to compressible flows where pressure can be computed from equation of state. We do not have any such independent equation for pressure for incompressible flow problems. So, in this case, if you do not have an equation for a variable, and it is one of the most important flow variables involved which drives our flow, what do we do? So, suppose we are dealing with an isothermal flow. So, there we will have a set of 4 equations, continuity equation, so its divergence of V is equal to 0, and 3 equations for each of the velocity components, but there is no equation for pressure. So, we have got, though the unknowns are for pressure plus 3 velocity components, and we have also got 4 equations available to us, but continuity equation cannot be used directly because it does not involve pressure. So, it cannot be used as equation for pressure, and it essentially represents a kinematic constant. So, we have to do some manipulations to derive a equation for pressure using our continuity equation. So, that is what it is. The way out of this difficulty of an independent equation for pressure is to construct the pressure field so as to guarantee the satisfaction of continuity equation. So, we will try to construct a pressure field whose solution would guarantee, or if you use that pressure field in a momentum equation and solve for the velocity field, that velocity field is guaranteed to satisfy continuity equation. That is to say, it will our mass conservation is enforced. So, how do we do it? How do we achieve this objective? To achieve this objective, we combine the momentum and continuity equations to obtain an equation for pressure, which is in the form of a Poisson equation, and hence it is commonly referred to as pressure Poisson equation. How do we obtain this equation? Let us have a detailed look at it. Let us write our continuity and momentum equations. For incompressible flow. So, our continuity equation is simply divergence of V is equal to 0, or in indicial notation we can write it as del V I over del x I is equal to 0. Next, our momentum equations. Del of rho V over del T plus divergence of rho V V is equal to minus gradient of P plus divergence of tau rho times P. Now, let us rearrange the terms here. So, let us rearrange, keep pressure on the left hand side. So, rearrange momentum equation. So, we can write this as gradient of P is equal to minus del of rho V over del T divergence of rho V V and the remaining terms. For simplifying our algebra, let us write this equation in Cartesian tensor notation. So, left hand side is del P over del x I minus within big brackets del of rho V I over del T. We have retained a rho here, but rho, please realize that we are dealing with incompressible flows, is just a constant value. Del over del x j of rho V I V j del over del x j of tau I j minus rho B I. Now, let us take divergence of this equation, because in continuity equation that is what we have got. So, divergence operator sitting there. So, taking divergence of momentum equation, so we will apply to this rearranged form. So, what do we get? Del over del x I del P over del x I is equal to minus del over del x I of del by del T of rho V I minus del over del x I of or rather we can write it as del 2 of rho vi vj divided by del xi del xj minus del 2 tau ij over del xi del xj minus del over del xi of rho bi. Sorry, these last two terms would have positive signs. Now, let us have a look at each term in this equation 5 separately. This del over del xi del over del t of rho vi. This we can exchange this temporal and spatial derivative. So, we can write it as del by del t. Rho is a constant, so we can take it out. Rho del vi over del xi. Del vi over del xi, that is divergence of velocity field, which is 0 for incompressible flow. So, this term evaluates to 0. Okay. So, therefore, what do we get? Del over del xi of del p over del xi is equal to minus del 2 over del xi del xj of rho vi vj plus del 2 tau ij over del xi del xj plus del of rho bi over del xi. Now, this equation has a form very similar to our Poisson equation. So, what we have got on the left hand side, we have got the Laplacian for p, on the right hand side this represents a sort of a source term. So, this is our Poisson equation, wherein we have still maintained a possibility that viscosity may not be constant. In fact, we will get a simplified form. So, if viscosity were constant, is assumed constant, then what happens? Our del over del xj of tau ij, this reduces to mu times del 2 vi over del xj del xj. So, if you apply del xi, therefore, del over del xi of del over del xj tau ij, this is mu times del 2 del xj del xj of del vi over del xj. So, this also vanishes because of continuity. So, we get a very simple form for our pressure Poisson equation. Similarly, our body force term that would normally be a gradient of a scalar field this body force is usually gradient of a scalar field. You can quickly verify it for the gravitational force field, which is because of a gravitational potential. Hence, this divergence would be 0. So, del over del xi of rho bi is 0. So, therefore, for constant viscosity flows, that is to say, if we are dealing with homogeneous isotropic and isothermal flows, our pressure Poisson equation takes a very simple form, del over del xi del p over del xi is equal to minus del over del xi of del rho vi vj del xj. So, this is the final form for the pressure Poisson equation for the flows with constant viscosity. Remember, in our derivation what we have done, we have started off with momentum equation. So, this inner derivative of p in our Laplacian operator. So, this side, this is Laplacian of pressure filled p. The first operator, this Laplacian we can write as del by del xi, that is outer one, so outer, and then we have got this inner one, del over del xi p. This inner operator is from a momentum equation, okay, and the outer, the divergence, this comes from continuity equation, because that is what we motivated us to take the divergence. We would apply the same operator which we would use for our continuity equation, and this has got some important consequences which we must take care of in our numerical implementation. So, simplified pressure Poisson equation, just a summary of what we have derived, del over del xi of del p over del xi is equal to minus del over del xi of, within brackets, del of rho vi vj over del xj. And I have purposely put that these two operators separately, so that the outer del over del xi clearly indicates that this is a divergence operator coming from our continuity equation, and the inner derivative del p over del xi, or here del of del xj of rho vi vj, these are linked to our momentum equation. So, we should be aware of it, that Laplacian pressure Poisson equation is the product of the divergence operator originating from the continuity equation and the gradient operator of the momentum equation. So, to maintain numerical consistency, it is essential that whenever in whatever discretization scheme we use for approximation of pressure Poisson equation, that must be defined as a product of the approximations of divergence for continuity equations and gradient operator which we would use in our momentum equation. If this is not taken care of, the satisfaction of continuity cannot be guaranteed by our numerical solution. We will just take a brief algorithmic look at the solution of our compressible flows. We will combine continuity, momentum and energy equations into a generic vector equations, that is what is normally done, and then we will discretize this generic equation. Usually the simplest way would be to choose an appropriate explicit time integration scheme and obtain the solution at the next time step in conjunction with suitable equation of the state to get our pressure. Similarly, we can also use our solution variables at a given time instant to calculate the viscosity and conductivity which is required, and the primitive variables, that is density would be solved, that will be part of one of the components of a generic vector unknown, but other components of that vector unknown would be rho u, rho v and rho w, and then total energy. So, the primitive variables, they would be obtained from this generic solution vector. Rho obtained directly, u is obtained by taking the ratio of rho u by rho. Similarly, rho v by rho would give us v component, and rho w by rho would give us the w component. Substitute for the magnitude of the velocity in our total energy equation, we can get E, that is internal energy. U is equal to CVT, that is T is equal to E by CV to obtain the temperature field, and so on. So, we run out of time in this lecture. Maybe some of the details might have a look at in future lectures, time permitting. For further details for the time being, I would refer you to the references. Read the book by Chung on computational fluid dynamics or computational methods for fluid dynamics by Ferziger. The State and the book, which is a beautiful introduction to computational fluid dynamics, that is Introduction to Computational Fluid Dynamics by J.D. Anderson, and that is specifically useful for compressible flow simulations. So, please have a look at the solution algorithms for the compressible flows in Anderson's book.